Hi Math 111. In this video for section 2.1 we're going to continue our discussion with functions, and what I'd like to do first is to recall that we have this special notation, right? We have this f of x notation here, okay, to denote a function. Let's make sure my pen's not too big. Good. Okay, so we have this notation f of x, remember, and that's how we read that, right? We read this as f of x. That's how we would read it to ourselves, right? If we were to say that f of x, right? And remember that the parentheses, they are not multiplication parentheses, they are what we call function parentheses, right? So this does not say f times x, it says f of x, right? And remember what this means. This notation here means the output of the function f when the input is x. And again, an equivalent way to write that would be something like this, right? Sorry, my pen's being a little weird. So this notation here is equivalent to, this y equals f of x is equivalent to f of x, and it means the same thing. The output of the function f is y when the input is x, right? So the output is y when the input is x. And that just helps reiterate or sort of emphasize the relationship between the inputs and the outputs here, right? So sometimes what we do is we call these inputs and outputs special names, and we've already said that when we have this sort of mapping with the bubbles like this, right? When we have sort of the inputs here, right? So inputs. And then we have sort of this mapping here, this sort of function f that sort of takes the inputs and gives corresponding outputs, right? We've already talked about how we can call the inputs domain, and we can call the outputs the range, right? But what we can also do is say that this variable x here could also be called the independent variable, right? Because x is a variable and it is sort of the starting place for us, right? The value for x's come from this first bubble here, right? So these are like the x's over here, right? And we could also, like I said, we could call these the independent variable. My pen is being a little weird. I'm trying this on my computer at home, so I'm getting used to the new speed of the pen on a different computer. So we could call this also the independent variable, and since the output, of course, depends upon what kind of an input you plugged in, then we could call these outputs over here the y's, right? So these outputs are the y's. Okay, we could call these the dependent variable. Because, of course, which y value it is depends upon what input you picked. Variable. There we go. Great. So it's convenient to also think about this function f as what your book likes to call a little machine, right? So it's convenient maybe to think about that there's this box, right? And this is like the function box f, right? And it's maybe some sort of machine and it has a rule or something. And what goes into it, what goes into the function here, and maybe a little tube, right, or something. Okay, this is where the input goes, right? This is what where the value of x goes, right? The value of x goes into this function. The function has some sort of rule that works on it, 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 something like that. And then out to this other side over here comes the output, right? And there's this little box here, okay? There's this little box, and it has some sort of a rule, okay, that says, I don't know, maybe the rule is something like, maybe the function is defined by something like, it says to take the value of x, maybe it says triple it, and then add 1. Right? That could be a perfectly valid rule, okay? So that rule would say you take the input, you triple it, and then you add 1, and that would be the corresponding output, right? That would be the output, the value of the function when the input is x, okay? So thinking about it in this way can help you think about this input-output relationship where there's this function that acts on the input, right? What's important to remember about this machine, though, is that you're only allowed to plug in certain kinds of inputs here, right? There's maybe only values of x that have a certain kind of an output, right? Maybe there's an input, maybe there's like a number you can't plug in here so that the machine can work on it and spit it out, right? So and those are the values, remember, that come from the domain, right? From this first bubble here. Any value of x that comes from the domain, from this bubble here, is able to be plugged in and then have an output correspondingly spit out by this machine here. Okay, and also remember, because this is a function, when you plug in something from the domain, right, when you plug in something in input, when you plug in something from the domain, from this first bubble here, right, you only get one thing coming out of this machine. Okay, one thing is spit out at a time. Okay, great. So maybe let's do an example here, because I know that I've given you on your worksheet some practice calculating outputs of a function, right, or calculating what the value of a function is for a given input. That those words are synonymous, remember. The value of a function is the same as the output of the function for a given input. So let's take our example here, this f of x equals 3x plus 1. Okay, so using this function here, let's find a couple values of the function, or outputs, right? So if I said I want to know what is f of 0, okay? This is saying what the value of the function when the input is 0. So what I do, remember, is, well, I want to know if this is the rule here. Remember, I'm using this function, okay? If this is the rule that says you take the input, you triple it, and add 1, well, when I take the input, which is 0, and I triple that, well, that means just to do what? I triple 0, and then I add 1, okay? In essence, what we really did here is replace this x with a 0, right? And so we rewrite that expression in algebra right there as 3 times the input plus 0, which is 3 times 0. 3 times the input plus 1. I don't know why I said 0. So 3 times 0 plus 1, right? And so now this is just, what? 3 times 0 is 0, plus 1 is 1, right? So the output of the function when the input is 0 is 1, right? So in this like machine idea here, if you input a 0 on this left side here into the inside, the function would work on it, and then it would output the number 1. Okay, great. So let's see, what about f of like -1? Good. So again, we triple the input, and then we add 1. Okay, 3 times -1 is -3, plus 1 is -2. Okay, but we don't have to do this just with numbers, right? I could say, what is f of, and this is going to seem silly, but what is f of happy face? Okay, you can plug in whatever as long as it's in the domain of the function, right? Okay, this may seem a little bit weird, right? But what does it say to do? The function says you do what? Triple the input and add 1. So I do 3 times happy face, plus 1. Okay, now of course this doesn't have any sort of numerical meaning to us, right? Okay, but what I'm trying to show you here is that you can, whatever you plug in here, as long as it's allowed to be plugged in, as long as it's something coming from the domain, right? You can plug it in and then compute it, right? So if I plugged in happy face, it's 3 times happy face plus 1, right? If I wanted to plug in f of square, then it would be 3 times square plus 1. Okay, so maybe when I plug in something like f of 2x, okay, that now this should not make us nervous, because remember, we just plugged in something before, and what does it say to do? It says to triple the input, that's our rule, triple the input and then add 1. So our input is blah, it's 2x, right? So we do what? Triple the input and then I add 1. Okay, so it says what? Triple the input, see the form is all the same, and then I add 1. Okay, well it turns out this one we can actually rewrite a little bit simpler, because 3 times 2x is what? 6x, so this is 6x plus 1. Okay, and again, the output for the input being 2x is not a specific number, okay, but that's okay, right? Remember, we just have to say for an input there is a given output. We got a unique output, and so this is still fine, right? Just like with the happy face and the square thing, we actually get something out, right? It's not maybe a number like you like to see, but it's still something, right? We got something. Good. Okay, so now what I'd like to do is talk about two different forms of equations that maybe you haven't thought about before. And here, what we need to do is emphasize two different forms of what are called explicit versus implicit forms. Okay, so implicit versus explicit. Okay, so the idea here between these two forms, right, these two forms of an equation, is that in an implicit equation, it's not solved for y equals, right? These are going to be equations still in two variables, right? There are going to be equations of x and y. So maybe these are still equations using x and y. Okay, but in the implicit one, it's not solved for y. It doesn't say y equals. Okay, so in an implicit equation, okay, it's not solved for y. And let me give you an example of something like that. That would be something like this: 3x plus y equals 14. Okay, this is an equation between x and y here, but it's not explicit. It's an implicit equation, right? It's an implicit equation because it is not solved for y, right? It's 3x plus y equals 14. The x's and y's are all sort of mixed up over on this side. Alternatively, an explicit equation is solved for y. Okay, so this one will say y equals. Okay, so I could take this implicitly written here, this 3x plus y equals 14, and I could write it explicitly by solving it for y. So the equation y equals negative 3x plus 14, that is an explicit equation. Okay, because it says y equals, right? Okay, so again, solving for y means the equation says y equals blah blah blah, right? Okay, so that's a fundamental difference between these two right here. And so having these two here can help us determine if an equation that we're given represents a function, right? So how can we do that? So we can determine if, let's see, how do I want to write this? So we'll say an equation is a function if it can be written in terms of y equals. And what I mean by that is if it can be written explicitly. Okay? So, for example, something like what we had over here, right, this 3x plus y equals 14, that could be solved for y, right? It could be written y equals negative 3x plus 14. Okay, so what that means is that this equation right here represents a function, right? And so if I change my color here, right, because I was able to solve for y explicitly, right, and write it as y equals, what that means is that this is in fact a function. Okay, so that is a function. Alternatively, what if I write something like x to the third plus xy plus y squared minus 16 equals 0. Okay, if I write something like this here, it's not possible for us to solve this y equals, right? Go ahead and try, right? There's no way we can get this to say y equals blah, 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 blah in terms of x, right? We can't isolate the y, okay? So the trouble here is we can't isolate the y. Okay, and because we can't isolate the y in this equation, what that means is that this equation does not represent a function. Okay, so that means this is not a function. Okay, so what that means is we can't use any of that f of x notation here, because remember that f of x notation is reserved explicitly for functions, right? So we can't write this equation, this x to the third plus xy plus y squared minus 16 equals 0. We can't write that in terms of y equals or f of x equals stuff, right? I can't use that notation because this is not a function. And it's not a function because I cannot write this equation explicitly. I cannot write it y equals and have it just y all by itself on one side and only x's on the other side. Okay, so we can use that as a way to algebraically determine if we have a function, but for right now we'll stop with that video, and we'll finish 2.1 in our next video.